Okay, so what I want to discuss is what people call matter fields, which is anything except the Goldstone bosons. And the classic example are baryons, because you can do pion, because pion-nucleon scattering were the famous experiments at the beginning, which were resolving the structure of the strong interactions, but you can have mesons containing heavy quarks or whatever. So first of all, in a generic case, you have some symmetry G broken down to H. The baryons, for example, or the rho mesons or any of the hadrons are some non-perturbative bound state. And the symmetry G has been broken down to H. So there's no sense in which these matter fields have any transformation under G. They only have a form, let's say, representations of H. And what that means in QCD is that they only form representations of SU3 vectors. So the baryons are octets, but you cannot specify how they transform under chiral SU3 left cross SU3 right. But when people say they're octets, they mean they're octets under SU3 vector. And the baryon matrix, so the octets are, SU3 can be written as traceless 3x3 matrix, and in that notation, the standard baryon representations are sigma minus, C minus, sigma plus, minus 1 over root 2. So they look very similar to the structure of the pion Lagrangian. Okay, so what in the meson case was pions becomes the sigma 0, sigma minus, and sigma plus. The eta is now the lambda, and then the k plus k0 is the proton neutron here, and the k0 bar k minus is the xi. And we know they transform under as an adjoint, so B goes to V dagger when you make a transformation where L is equal to R is equal to V. But we don't know how they transform under chiral SU3 cross SU3. Now, when we put them in the chiral Lagrangian, we need a transformation property for them under chiral SU3 cross SU3 because the mesons and everything else transform under it, and we have to write down an invariant Lagrangian. So this was the second paper in the Callan-Coleman-West Zumino series. And the answer is you make them transform under what we were calling H. So remember, C went to L, CH dagger equals H, CR dagger. So any SU3 cross SU3 transformation produces some H by this formula. And generically in the Gmod H symmetry breaking, we also saw that the transformation of the capital Xi had an H in it. And the baryon transforms the adjoint as B, as HBH dagger, because when L is equal to R is equal to H, then here, everything here is an H, and then this transforms correctly under SU3 vector. And there are other choices you could make. So this is the nicest one. The Feynman rules and everything. Sorry, other choices are nice, but historically people, let's suppose you said B left went to L, B left L dagger. Well, you can do that because under the SU3 vector transformation where L is equal to R is equal to V, this is also an adjoint. Let's put some other symbol here, B twiddle. Okay. But if I multiply this, let's see, if I take C, B, C dagger, the original left, and make this B twiddle left, then the B left has an L here, and did I have this backwards, I guess? C dagger this way. So B left has an L dagger on the right, and then you multiply by a C, and the C basically converts the L to the H dagger, and on this side it converts it to the C. So this B, what am I doing? I'm doing it backwards, am I? The twiddle is here. Yeah, the twiddle is here. So this is the connection between the B twiddle left and B, the left-handed part of B. And if you, let's say, said B twiddle right, went to R, B twiddle right, R dagger, then the original B right field would be C, B twiddle right. Something's wrong here. Which one? Both are. Which ones are? How can? Wait. The B twiddle has a L dagger here, right? So then I have to multiply it by the C to kill the L. And on this, it's this way. Is that right? Who knows? And then this was backwards. Okay, but remember that the C field was the exponential of I pi over F, which starts as 1 plus stuff. So at leading order, BL is B twiddle L, and then there are pion corrections. So this is simply a field redefinition. And any one of these you pick will have the same S matrix, even though the Feynman rules may differ. So what CCWZ said was, well, just make it transform under H, and then you can apply it to everything. Tim Cohen said he would discuss field redefinitions next week, so maybe you can ask him questions on that. So now when you introduce these baryons, there are two other quantities which are useful to define. So one is V mu, which is defined as 1/2 C d mu C dagger plus C dagger d mu C. And the other is called A mu, which is I over 2 C d mu C dagger minus C dagger d mu C. Now, when you apply parity, pions are pseudoscalars, so pions go to minus pions, and C becomes C dagger, and C dagger becomes C if you just flip the sign of the pion. So if you look at this term, the first one is, when you apply parity, is parity even, that's why it's called vector, and this one's parity odd, which is why it's called an axial vector. And A mu is Hermitian, and V mu is anti-Hermitian. And if you expand them out, at leading order in pions, this one becomes d mu pi over F plus pi cubed. And this one is 1 over 2F squared pi d mu pi plus order pi to the 4th. So the axial one involves odd numbers of pion fields, and the vector one involves even numbers of pion fields by parity. So if I apply my chiral transformation, so dC transforms this way. I'm sorry, C transforms this way. So dC under a under this chiral rotation. Remember, L is a global symmetry, but both C and H can depend on X. So dxc goes to L dc H dagger plus LC dH dagger. But dH dagger, H dagger is the inverse of H, is minus H dagger dH H dagger. And therefore, if I then take C dagger dc, so then I multiply by the dagger of this, right? So you get H, and then the L dagger cancels the L, and you get C dagger dc. And here you have an H dagger. And on the second term, when you take this, the L and the C both cancel, and the H also cancels, and you get minus dH H dagger. And then I can apply parity, or equivalently, I can use the second form of the relation just to show that C dc dagger goes to H C dc dagger H dagger minus dH H dagger. H is a vector, so under parity H becomes H, but C and C dagger are swapped. Okay, is this clear? Okay, so the key thing is that L and R are constant matrices, but H does depend on X, and you have to differentiate the H. But now you can see from here that V mu goes to H V mu H dagger minus dH H dagger, because you're just averaging these two. And A mu goes to H A mu H dagger. So A mu just transforms like an adjoint. It's a useful axial vector to have around. It's allowed to be there in the chiral Lagrangian. It's just a combination of C's and C daggers. But V transforms like a gauge field. And if I can define a chiral covariant derivative, which is d mu plus V mu. And if I have a field psi which transforms with H, okay, and remember H depends on X, so this is like a local transformation, then d mu psi will transform like H d mu psi. So this allows you to define covariant derivatives for objects which transform under H, because under H it looks like it's a local transformation since H depends on X. But with this V mu field, you can define covariant derivatives. So if the baryon transforms like the adjoint, then the covariant derivative on the baryon is d mu B plus V mu commutator B, because you have, the H on one side gives you the V mu on the left, and the H dagger on the other side gives you minus V mu on the right. So this is just the standard way of doing covariant derivatives for adjoints. So now I could try and write down the chiral Lagrangian. And for example, I could have the trace of B bar ID slash minus the baryon mass times B. And then the standard notation is that there's a coupling constant D trace of B bar gamma mu gamma phi B times, gamma mu times the anti-commutator of A mu with B. So remember that B is a 3 by 3 matrix. These C's and A mu's and V mu's are all 3 by 3 matrices. So, and A mu is an axial vector. You want to conserve parity because the strong interactions are parity conserving. So the EFT has to have the same symmetries, and it preserves parity. And the usual convention for these couplings is the trace of B bar gamma mu gamma 5, A mu commutator B. So when you take the trace of these three matrices, You can always put the B bar as the first one, but then you can either have A mu B or B A mu. And rather than write those terms separately, people write them as the linear combination of A mu B plus B A mu and A mu B minus B A mu. And this is called the D term and the F term. Because in SU3, if you take the commutator of two generators, you get the F symbol. And if you take the anti-commutator of two generators, you get the D symbol. And then, of course, we have the usual meson chiral Lagrangian, which we wrote down and discussed at length. So these are just the additional baryon terms. Now, A mu here starts off as d mu pi. So now these interaction terms are order p rather than order p squared. There's only one derivative in those terms. Okay, so in the matter sector, or in the baryon sector, the chiral Lagrangian starts at order p, not order p squared. The other thing you find, if you start doing loops with this, is that when you start doing loop diagrams with pions, you get the mass mb in the propagator. And the baryon mass is about 1 GeV. And you can get factors of the baryon mass, and it messes up the whole chiral power counting, because now you have a big scale where, which is comparable to the scale of chiral symmetry breaking. So if you naively do baryon chiral perturbation theory, you'll run into trouble. However, what chiral perturbation theory can, okay, so an example of that is if you did proton-proton annihilation, for example, to a whole bunch of pions, that is not something you can calculate reliably in chiral perturbation theory, because 2 GeV of energy is being transferred to the pions. However, if you do pion-baryon scattering, baryon number is conserved, so the baryon number runs through the line. And all that really matters is not the mass of the baryon, because that's sort of flowing through the diagram. It's the momentum transfer of the baryon, and that if the pion energy, momenta or energies are a few hundred MeV, you should be able to apply chiral perturbation theory here. So the solution to getting a good expansion with a good power counting is exactly what was done, Matthias did for HQET. This is the same argument as for HQET. You have a heavy quark, but it's interacting with soft gluons, or soft degrees of freedom. Here you have a heavy baryon, it's interacting with soft pions. And so what you do is you define a field B sub V of x. Okay, so this should be familiar. It's exactly the same. MB V dot x, 1 plus V slash over 2 times the baryon. So you write the chiral Lagrangian not in terms of the baryon field, but in terms of this velocity-dependent baryon field. And it's useful to think of everything in some frame. One V mu is 1, 0, 0, 0, which is called the rest frame. And so what we're doing is we're saying the baryon for momentum has a piece in it, which is MB 0, 0, 0, which is basically one baryon sitting at rest with mass big M, but then it can have some interactions with K mu, where K mu is order P, and P is much, much less than lambda chi. So you're hitting this heavy baryon, which is sitting there with soft pions, and moves a little bit. And now the chiral expansion is valid. Okay, is this clear? Now, I could go through, like in heavy quark effective theory, and write down, yeah. Yeah, just substitute into this Lagrangian. That's correct. So what people, the reason they like this other notation was that they got sigmas rather than x's. MB is, yeah, MB is we haven't put in any quark mass symmetry breaking, so this MB is like some average mass of this whole baryon multiplet.
But then you get non-derivative interaction.
Yeah, but the fact that it's a non-derivative interaction is a fake, because you can go to another basis where you can see explicit. That's the field redefinition. So this is why this H basis is useful, is because in the H basis, it's explicitly derivatively coupled. But in the other form, it doesn't have to be. Okay, so, okay, this is a long story. For right now, these are the baryons, and if you're working with the pion excitations, you can imagine that this baryon multiplet's here, and let's say there's some other, some excited baryons or some M prime or something, and there's some gap. And for right now, you would say that to do chiral perturbation theory, you have to make sure that the energy isn't sufficient to excite the state. Now, for the case of the deltas, which are strongly coupled, what you can do is you can actually include another multiplet, which is the, I think we call them T sub V mu, which is because the deltas and stuff are spin 3 halves, which has the delta, the sigma star, the C star, and the omega, and this is the 10-dimensional representation of SU3. And then what happens is you can have couplings like T bar mu, A mu B, or whatever, which would give you proton, pi, delta type couplings. And this is actually very important because it turns out in large N QCD, you can prove, so these are papers, so I have some, I don't have that, there's some Lesouche lectures on large N, and Elizabeth has some lectures on large N baryons. And what happens is that if you look at these vertices are order root N color and the strengths become large as N color gets large. And if you start doing barrel chiral perturbation theory and you do loops like this is order N color. And if you forget about N color and just do it in for three colors that we're using the known pi N couplings, these loop corrections are big. What large N does is it puts the nucleons and the deltas into a multiplet. Essentially, if you think of the Skirm model, you get an infinite tower of states. Anyway, we were able to show there was a symmetry of QCD where all of these things form one irreducible representation, and the NN pi couplings and the N delta pi couplings and the delta delta pi couplings are all related by the symmetry. So there's no extra free parameter. There's one free parameter. So in fact, not only are they related, the F to D ratio is predicted to be 2/3 plus order 1 over N color squared, which agrees very well with the experimental value, which is about 0.6, I think. And then when you do this, you can do chiral perturbation theory where there's intermediate nucleon states and intermediate delta states. And these couplings are such that all of this stuff cancels and the corrections become order 1 over N color, as you might expect for loops. And so there's a whole, so there's a whole series of papers which we have on doing combining large N with chiral perturbation theory for baryons, and you have to do it basically for something like this because otherwise these corrections are big. So you can just look up what we did. But for right now, let's just forget about this and just learn how to do this original, just set up the Feynman rules basically for that. This only works if the momentum transfers are small. So in the rest frame of the baryon, the pion has to be soft, otherwise it's not valid. Just like HQET doesn't work if you hit this meson system with some energetic gluon. Okay, so one thing you could do is write down this QCD Lagrangian, the EFT Lagrangian for the baryons, and then make the switch to this velocity-dependent field exactly as Matthias did for the heavy quarks. But in the case of baryon chiral perturbation theory, we don't actually know what this Lagrangian is. We just have all of these arbitrary parameters. And then you can do the work and convert. But that's just a waste of energy because since you don't know what the original starting point is, you might as well just directly write down the most general Lagrangian using B sub V directly and just put in all the arbitrary coefficients there instead of doing two steps. In the quark case, we know the fundamental theory, QCD, we know the couplings. There's only one, basically, the D slash. And then you can go calculate the heavy quark Lagrangian systematically in powers of 1/m. But here, since we don't know any of these coefficients, we can just write things directly. And the velocity-dependent Lagrangian looks very similar to that. So it's the trace. So remember from Matthias's lectures that the kinetic term now for a heavy quark, and in this case a heavy baryon, becomes linear in velocity with a single derivative IV dot d. This is basically the energy. So when you do perturbation theory, the propagators give you one of the energy, which are the standard energy denominators of perturbation theory. So it's B sub V. And that D term there becomes the trace. It looks just the same, basically. Gamma V, gamma 5, A mu B sub V. That's the F term. Let me not write the whole thing down. And then now we have corrections which can be order 1/mb, and we can have corrections which are order 1/lambda chi, coming from the 1/m expansion and the chiral expansion. In the case of real baryons, these two are comparable in size, so you can just take the expansion parameter to be 1/lambda chi and just combine the two terms. But if you were working with heavy mesons, like the B meson and stuff, then there are pieces which are 1/lambda chi, and then there are some pieces which are 1/m. We'll discuss this. And the reason you can do all this is that if you shift the energies of the, where's it gone? This term basically shifts the energies of all the baryons by mb. You're removing the non-relativistic rest energy of the baryon and writing all energies relative to this. And that energy just goes flowing through the diagram. And so, this is the same argument as why HQET works as well. So the baryon propagator is now I over V dot K from this kinetic energy term. Yeah. Yeah, it's P over lambda chi. Yeah, that's what it's going to be. That's right. Okay, so now we saw when we were doing Weinberg's power counting rule for mesons that the meson propagators were 1/p squared. Here, the baryon propagators are 1/p, or K I call them. And I'm not going to go through, you can repeat the whole power counting rule for the baryon sector, and the answer is that the graphs go like P to the D, where D minus 1 is the sum of, is 2L plus the sum on K, Vk, K minus 2, where this is over the meson Lagrangian, plus the sum on K, Vk, maybe it's not the best note, I called it Wk, okay. Where this is the baryon Lagrangian. Because there's still here the meson Lagrangian. So like, for example, the trace of d mu u dagger, there's no baryon fields in that. So that's what I mean by the VKs. They're coming from the meson Lagrangian, and the WKs are things from here where there's a baryon. And this looks very similar to Weinberg's power counting argument. You get this 2L for the number of loops. You get this K-2 type stuff from the mesons, exactly in Weinberg's power counting argument. But there's a difference now between meson and baryon terms. The baryon, so these interactions, for example, come with a K-1. But we know in the meson sector that K has to be bigger than or equal to 2. And we know in the baryon sector that K has to be bigger than or equal to 1. So you're still adding things which are positive. So you should derive this as just, again, counting loops and internal lines. But here you have to distinguish between internal pion lines and internal baryon lines, and then use the same topological identities to work out what's happening. But again, every time you have a loop, you move 2 powers away, 2 powers more in the power counting, etc. And the naive dimensional analysis formula that I told you, yeah, there are only pion loops because baryon number is conserved and the baryon line just goes through the diagram. If you were to do something like this and put a baryon loop here, well, there's intermediate energy of 2 MB. None of this is you can't apply chiral perturbation theory to this. So you couldn't do like pi-pi scattering and produce BB bar or something. It was just, yeah, the whole thing. People do it, but the theory is not valid. That's right, okay. So the counting we had before was that we got some lambda chi squared f squared pi over f to the a, derivatives over lambda chi to the b. And now the only new feature is that you have a baryon over f square root of lambda chi to the c, or equivalently, this is 4 pi times the baryon field over lambda chi to the 3/2 to the c. So this is consistent with our old power counting. There's a 4 pi for every field, and then this gives you the power counting. Okay, so this is the setup. And the leading interactions are order p. Oh, I should say one other thing, which is in the v dot d, the v dot d is v dot derivative plus v dot v mu. So, I mean, that's what this thing means. It's the chiral covariant derivative. Okay. So now let's do an example. So I'm going to do the pion-nucleon scattering length. So pion scattering at threshold. We already did pi-pi scattering, so this is the nucleon version. Okay, so the diagrams you get at order p are this, plus the cross graph, plus the 2 pion interaction. This is from the v dot d term. The v mu starts at 2 pions. And so this is the order p scattering amplitude. I mean, here you might think there are 2 vertices each of order p, but then the propagator is order 1 over p. And from that power counting rule, tree graphs with only order p interactions gives you a net result, which is order p. So these are the graphs. I mean, but the a mu is order p, so that would be things. You can have things at order p squared. I'm just sticking with p. Okay, A mu is d mu pi. So actually, I should do some other thing first. So I'm going to, just to avoid problems, I'm going to just do SU2 chiral perturbation theory. So we only have the pions, no kaons and etas. And then the nucleons are the column vector, proton and neutron only. The only difference is that now you don't have two invariants. There's no trace because now B is a column vector, B bar is a row vector. So you have this term, and both of them, they're not two independent invariants. So you only have GA, B bar V, gamma mu, gamma 5, A mu BV, because to get an adjoint from a fundamental and an anti-fundamental, there's only one way. Whereas if you want to combine three adjoints, there are two. There's an F invariant and a D invariant. So this just simplifies some of the group theory. And so the coupling we have, this vertex, so this dot is GA, B bar V, gamma mu gamma 5, B sub V. Okay, I guess I can put the d mu pi inside. D mu pi, B sub V, GA over F. Okay, this is a square matrix, and then that's a row vector and a column vector. Now, as far as the Lorentz structure is concerned, it's B bar, or the spinors. You have B bar V, gamma mu, gamma 5, B sub V. So let's look at that. So I have B bar V. Now, I know that B sub V slash satisfies V slash, sorry, E equals B sub V. Now, maybe the easiest way to understand what I'm saying is, suppose I work in the rest frame where V mu is 1, 0, 0, 0, then V slash is just gamma 0. And when you're doing SET, it's more convenient to use the Weil basis. When you're doing HQET, it's more convenient to use the so-called non-relativistic basis where gamma 0 is 1, 0, 0, minus 1. And you know that in this basis, the way the spinors work out is for fermions which are slowly moving. This is the big component, and that's the small component of the Dirac spinor. And in fact, for a fermion at rest, this part is exactly 0. And that's the condition that V slash B is B, because if the eigenvalue is +1, it has to be in the upper block. It can't be in the lower block. Now you can look at what gamma mu gamma 5 is. And in this notation, gamma 5 is 0, 1, 1, 0. And gamma mu, gamma vector, I think is 0, sigma vector minus sigma vector 0. And here's gamma 0. And if you just work through it, you will see that B bar V gamma vector, gamma 5B, is the same thing as B bar V. So if you multiply this by the gamma 5, it puts these sigmas on the diagonal. And because the spinors are basically in the upper component, schematically I can say that this is just B bar V sigma BV. It's a bad notation, but what I mean by this is I'm picking out the two-component part of the spinor, which is in the upper block because of this. So in the frame where V is, this is in the frame where V is 1, 0, 0, 0, I'm writing B sub V as something in the upper block and 0, and I'm just calling this B sub V again. Maybe I should use a different notation. But it's the Pauli matrix. So pions coupled to baryons with a spin-dependent transition amplitude. But more importantly, B bar V gamma 0 gamma 5 B sub V is 0. because gamma 0 is diagonal, gamma 5 is off diagonal, so this is coupling the big to the small components, but the small components are 0. So, okay, any questions on this? Okay, so when I now look at the pion coupling, if I take a massive pion exactly at threshold, so that's what makes it easier to do this calculation. You can also do it away from threshold. There's a little bit more work. But the energy of the incoming pion is m pi 0, 0, 0. So it's at rest, basically. And the outgoing pion also has this momentum. D mu pi brings out the momentum of the pion. But d mu pi only has a 0 component, and gamma mu, gamma 5, the 0 component vanishes. So at threshold, the first two graphs are gone, exactly at threshold. So we work at threshold. And then the interaction term is b bar v I. I erased what I wanted, but okay. V dot v mu, but v mu we saw was 1 over 2f squared pi commutator d mu pi plus higher order stuff. So that's what I get. Okay, so that's coming from, where's it gone? It's coming from this term, using the fact that v mu is 1 over 2f squared pi commutator d mu pi. And if I write pi, as I call them, I think it's g, pi g tg, and this as pi h th, then I get b I b mu over 2f squared. I get pi g d mu pi h. And then the commutator of tg with th is I f gh c or f c gh times tc. So then I get b bar v tc e sub v. Okay, so that's because the commutator is a structure constant, and so this is what I get. And the pions transform as the adjoint representation under the flavor group, and I can write this. I just want to get the sign right, as Tc pi Hg. So if you take the representation matrix for pions for the generator TCHG, that can always be written, because it's the adjoint representation, as the structure constant minus IFCHG. And the structure constants are antisymmetric, so it's the same as the plus IFCGH. So I can replace this factor by the pion representation element. So I get, no, I'm doing SU2. But this part would work even for SU3. It would be the SU3 structure constant. But then the baryons would have this commutator and anti-commutator with the D and the F. So that's why I was sticking with SU2. It's easier. Where are we? So we have Tc pi Hg. Okay, and then I have I v mu over 2f squared. Actually, let's forget the v mu. I over 2f squared pi g v dot d pi h v bar dcb. Okay, I don't know if I Messed anything up. Okay, now what is B bar TCB? That's simply the generator, the flavor generator in the baryon sector. So I can call this TC baryon. It has some label for the initial baryon and the final baryon. And now I want the matrix element of this object in the, here. So here's the initial baryon, here's the final baryon, here's a pion coming in, here's a pion coming out. And let's see if I can get the sign right. So I said that, what did I do here? Okay, so let's say A comes in, pion of type A comes in, and a pion of type B goes out. So if a pion of type A comes in and a pion of type B goes out, I have 2 over f pi squared, TB dotted into TC pi, and A comes in, so let's say this is A, and that's B, and B goes out, then G is the index A, H is the index out, and the derivative acting on an outgoing pion gives me I P dot V, and the outgoing pion momentum is m pi, so I get I m pi. Now, there are 2 ways of contracting this with the pions. Either I contract G with the initial pion and H with the final pion, or I swap them. If I swap them, the V dot D is now on the initial pion, and acting on an incoming pion, you get minus IP on the derivative, and its energy is also E. So you get a minus sign, but then you have to swap the A and B indices on the T matrix, but that's a structure constant which is anti-symmetric, so you just get a 2 here. And if I have, yeah, and there's an extra I, because this is just from the e to the I action, every vertex has an I. So this is the vertex I. And so the net result is I get minus I over f squared, minus I over f squared TB dot TC m pi. Okay, so that's my amplitude. The pion nucleon scattering amplitude at threshold. Now I want to make a slight modification to this. So when you go from relativistic baryons to this non-relativistic formulation, in the non-relativistic formulation, you use with the velocity-dependent fields, you normalize the fields so that B dagger B is 1. That's the non-relativistic normalization. Whereas the relativistic field theory normalization, you normalize states to twice the energy. So there's an extra factor here of twice Mn from switching to the relativistic normalization. Okay, so it's like a trivial factor. Okay. Now, in the case of pions, we derive the scattering lengths, and so we're going to do the same thing here. And again, okay, so this is historically, people could have talked about the amplitude. They instead talk about the scattering length. So the scattering length yeah, that's what I mean by the dot product here. It means there was a sum in, oh, this should not be C, this should be pi. It should be the pi. And this should also be the pi. So, okay, so this is just some historical definition of minus A times the scattering amplitude over 8 pi m pi plus mn. This is just the sum of the 2 particle masses, and okay, 8 pi and so on. The I is just some definition. So So the scattering length is minus 1 over 8 pi f squared t pi dot tb. And then you get 2mn m pi over m pi plus mn. And in the case of pions, we define something in terms of this length L. So this, I mean, all of this is kind of trivial. It's just some conventions for how people quote the results. The L was defined as has units of length, and it's defined as m pi over 8 pi f squared. So you can see that there's an m pi over 8 pi f squared here. And if I pull that out, the scattering amplitude is minus L. The m pi over 8 pi f squared is gone. There's a 2 here, which I'll put along with the t pi dot tb. And then you have mn over m pi plus mn, and if I divide by mn on numerator and denominator, I get a 1 plus m pi over mn. So this is the Weinberg-Tomozawa formula for the pion scattering lengths. Now remember that in the case of the this A mu coupling, there's a parameter here which is GA, which is the so-called axial coupling. But the V mu term, because it's from the covariant derivative, has a coefficient of 1. It's fixed. So there's no free parameters in this V mu. There's no unknown coupling constant. It's exactly determined. So there's no free parameter here in the chiral Lagrangian. And the last thing you do is you say that 2 t pi dot tb is t pi plus tb squared minus t pi squared minus tb squared. The pion has isospin 1, so that's minus 2. The baryon has isospin a half, so that's minus 3/4. And then if I combine the pion and the nucleon in the isospin 1/2 channel, because if I combine 1 cross a half, I can either get isospin 1/2 or isospin 3/2. The value of 2 t pi dot tb is in the isospin 3/2 channel, it's minus 2. Sorry, in the isospin 1/2 channel, it's minus 2, and in the isospin 3/2 channel, it's plus 1. Okay, because in the isospin 1/2 channel, the first term becomes a half times 3/2, which is 3/4, which cancels the 3/4, and you get a minus 2. In the isospin 3/2 channel, the first term becomes 3/2 times 5/2, which is 15/4. Minus 3/4 is 3. Minus 2 is a plus 1. So the final result then is that the scattering length in the isospin 1/2 channel is 2L, 1 plus m pi over mn to the minus 1. In the 3/2 channel, this is minus L, 1 plus m pi over mn to the minus 1. And you also get the famous relation that A 1/2 plus 2A 3/2 is 0. Okay, so this is again a very famous calculation, probably in the 1960s, where Weinberg and Tomozawa using chiral perturbation theory, or well, it wasn't chiral perturbation theory then. They were using what's called PCAC, various soft pion theorems, were able to calculate the pi nucleon scattering lengths. It's a strongly interacting theory, but you can still calculate it. And maybe today it's not appreciated, but what is the result in terms of? It's in terms of L, which is 8 pi over f squared. And how did we get f? We got f from pi to mu nu decay, which is a weak decay. So if you think of what was done by these people, They took a weak interaction process to determine F, and from the weak decay of the pion, you could compute the strong interaction scattering length. Okay, which is a very non-trivial, especially if you don't know what the weak interactions are or the strong interactions or anything, you can still do this, and this agrees very well with the experiment. So here's an example of baryon chiral perturbation theory. I'm not going to do the loops or anything because really, I mean, you know how to do loop diagrams. The integrals are the same as ones you're used to. It's really the technology of setting up the formalism, and then you have to go calculate the corrections. Yeah, but they didn't know any of this, right? So F pi for them was the matrix element. Yeah, it was the matrix element of the strong interaction of these. It was the matrix element of the weak current between the vacuum and the one pion state. I mean, now we write it with quarks and stuff, but for them, that was just some J mu weak. They didn't know what it was, right? So that's. Yeah. Well, the B is in the fundamental. So this is in the isospin a half, and that's in the isospin 1. That's why we turned the structure constant, wherever it was, this. So that's what we're using. That's in the adjoint representation. You can do the same thing for SU3 because the F and D terms don't come in, and you'll get the same kind of result. And now you will have to dot the SU3. You would have to calculate the analog of TB dot T pi in the SU3 channels. That's all. The formula will be the same, basically. Yeah, so let's first start with GA. So then there's a coupling. So this is the proton-proton pi coupling, which is proportional, well, it's equal to GA d mu pi over F B bar V gamma phi B. So pi A, and then put the TA matrix here. So you can measure the proton-proton pion coupling or the proton-neutron pion coupling, et cetera. And there's one free parameter, which is GA, which is like 1.25 or something, which is determined from measurement, basically, experiment. And you can also get it because of the fact that if I now do a weak decay, this is the axial vector current, and it contributes to neutron to PE minus mu E. The axial vector matrix element in this decay, for a weak decay, has got a GA in it when you put in the spinners. So you can also measure it from the weak decays. And here in the SU3 case, it's similar. You have a whole bunch of these because you have you have the nucleon, the lambda, the sigma, and the Xi, and they couple to the same things with the pi. And then now there are two independent in SU3 invariants. So by measuring multiple ones of these, you can determine F and D. F plus D, I didn't do this, but the relation to the SU2 case is GA is F plus D. I'll do something similar with F and D, but this is 1.25, and F over D is about I forget the number, around 0.6 from experiment. So you fit all the weak decays in the various strong interaction pion, and get it. The weak decays is usually the best way to do it. You can just look at the particle data book, weak decays, and extract F and D. So it's not calculable from, it's a free parameter in the EFT. H and G goes from 1 through 3. C goes from 1 to 3. As a matrix has some, Yeah, R and S, and this R and S goes from 1 and goes to 1 and 2. So you think of this as acting as an operator acting on the space of pions and baryons. It's like combining angular momentum. It's the dot product of the isospin of the pi and the isospin of the B. The pion isospin generator is like raising and lowering operators acting on pi, and this is like raising and lowering on B. And now this is like combining angular momentum. That's what you're doing. So it's just replace angular momentum by isospin. So that's what's happening. So it's basically just an efficient way of putting in all the indices and doing the Clebsch-Gordon algebra. Sorry, to what? No. The V mu is even in pions, and because it's a vector, and the A mu is odd in pions. So the V mu term won't contribute to the 3-point function, and the A mu term doesn't contribute to. The V mu term doesn't contribute to the 1 pion. What did I say? V mu does not contribute to 1 pion, and A mu does not contribute to 2 pions. Yeah, because we have parity, so that helps in this case. Pions are pseudoscalars, they're parity odd. So typically you'll see, even in the meson case, we had some operators which were even powers of pi and the others were odd powers of pi. Depending on whether it's a parity odd or parity even, basically. Yeah, go ahead. So, yeah, so what you do, okay, what I was going to do is just, so I think this is like time's up, right? So in the next part, I was just going to do a couple of things with baryon masses and then discuss this more general formalism with sources. But you don't need to do that. You can go calculate the weak current by making the infinitesimal transformation. And if you calculate the weak current here, or the axial current, so this answers his question as well. The axial current is B bar gamma mu gamma 5. And now there will be no A mu. It will be TA anticommutator B trace with a D plus the F term. And that's the axial current A mu axial is equal to this. So this is the formula for the axial current, and you obtain it by making the same way we did before. You make an infinitesimal transformation where L is e to the I epsilon L A TA, but now you make this a function of x and pick out d mu epsilon A and look at what J mu is. So you can go through the algebra and you get this. That's why this A mu is kind of nice. It also tells you what the weak current is. So now when I'm doing weak interactions, my current is J mu AV. It's V minus A, right? So that's what's coupling to the weak interactions. The vector current is coming from here, and there's no free parameter, and this is the statement that the vector current is not renormalized. So J mu vector A is just B bar V gamma mu TAB, and there's no parameter, it's 1. Now when you do the axial, so this just becomes, in the baryon, this just becomes B bar gamma mu B TAB. This one in the baryon becomes, if I just put the spinner, let's say, this becomes U bar gamma mu gamma 5B U. But then there's a Clebsch-Gordon coefficient, which is the trace of the final baryon TA anticommutator B with an F plus D trace of B bar TA commutator B. So you have to do these traces, just put in the baryon matrix, do this trace, read out the, let's say the proton sigma bar term, whatever it is, it's some F plus D or 3F plus D, whatever you get. And so this this piece is not a 1 anymore. You would have normally used gamma mu, you would have normally used u bar gamma mu 1 minus gamma 5 u. But now here, there's some number in here, which is some function of AF plus BD. And then you can calculate the weak decays and then fit to all of these weak decays, and you can extract F and D. So that's what you do. And there's two things you can do. You can measure the lifetime, which is some form factor, some 1 plus 3 GA squared, I think. And you can also look at the polarization in baryon 1 goes to baryon 2 L minus nu. You can look at the net polarization, which also, and the angular asymmetries, and they also determine this axial coupling. So there's some fits. You can do fits to extract this. Okay.